In this lesson, students will define the axis of symmetry, and we will reflect figures over the lines of reflection. So this is all about reflections and symmetry today. So let's first define what symmetry is. So two figures are considered symmetrical if they are mirror images of each other. And then these symmetrical images will have an axis of symmetry to them. Okay, so an axis of symmetry, we're going to define that. And that is essentially the line of reflection. So it's the line that the pre-image is reflected over. If I have a point A and I have an axis of symmetry or a line of reflection, I can reflect point A over that line, and it's going to be the same distance away on the other side. So the axis of symmetry, the line of reflection, will be right in the middle, and A prime will be the same distance away. The perpendicular, if I connect the two, the perpendicular distance, actually if I connect like this, the line connecting a pre-image and its image over a reflection will be perpendicular, and this length to the center will be the same as the other side. So reflected points will be the same distance away from the axis of symmetry. All right, and then the segment AA prime is going to be perpendicular to the line of symmetry. So I can say AA prime is going to be perpendicular. If I label that line L, it's going to be perpendicular to line L. Okay, we have four common lines of reflection in reference to the coordinate plane. So the first one is the x-axis. And so the symbol for reflecting over the x-axis, the symbol for reflection is a lowercase r, and then you write down the line of reflection as a subscript. So you could represent the x-axis by just calling it the x-axis, or a reflection over the line y is equal to 0. Because if you're looking at your x and y axis, that's going to be this guy right here if you're reflecting over that line. Okay, so that's the symbol. Let's say I have a point A and I reflect it over the x-axis. I'm now at A prime. Well, if you look at that intuitively, the only thing that changes is the y value. The x value stays in the same spot. It's still this distance away from the y-axis. So the rule is going to be x, y will map to x negative y. Okay, that's for the x-axis. The second line is going to be the y-axis. So that's in notation. You could say reflect across the y-axis, or reflect across the line x equals 0. And if I drew a picture of that, again we have our x and y axis, x and y. If I have point A and I reflect across the y-axis, then A prime is going to be on the other side. The y value doesn't change, but the x value is negated. So this rule is going to be x, y will map to negative x, y. Okay? So when you're reflecting across the y-axis, the y value doesn't change, only the x value does. So that's our second rule we can use. I'm going to box that in so you can find it. And then we have two more special lines that you don't see quite as often as these two. So the first special line is the line y is equal to x. And if we look at that, if I were to draw an x and y axis again, there's my x, there's my y. The line y equals x is going to be a 45-degree angle going through the first and third quadrant. So when you have a point A and you reflect across this line, the rule is you're basically switching the x and y components. So my rule, my symbol is r of y is equal to x, and the rule x, y is going to map to y, x. You're just going to switch them. Okay? And then the last special line is y is equal to negative x. And if I sketch that, that's going to be going in the opposite direction. So this is y is equal to negative x. This time when I have a point and I reflect it, it's the same distance away, perpendicular on the opposite side. You switch them and you negate them. So in symbols, it's reflection over y is equal to negative x. As a rule, x, y is going to map to negative y, negative x. So those are the four special lines. If you need to reflect over those lines, you can reuse these rules to do so. Okay, so here's a typical example. You're given triangle ABC and the coordinates, and I've graphed them over here. If you want to do this example on graph paper or just kind of sketch it to follow along, it's up to you. But the instructions are reflect triangle ABC over the y-axis. So in symbols, that means it would be R, y-axis, and then you would put triangle ABC. So we can do this visually, and then we can do this using the rules. If I am reflecting over the y-axis, that means the points are going to be the same distance away on the opposite side. And again, this is the y-axis. So if I start with A, I'm going to reflect him to the other side and label him A prime. For B, I'm going to be 3 units away on the other side. There's B prime. C, 1, 2, 3, 4, 1, 2, 3, 4. There's C prime. And there's my reflected image. If you didn't graph it, you can just use the rules, starting with the originals up here. It's always a good idea, if you have a problem like this, it's always a good idea to write down the new coordinates. So if I'm going to do that, I'm going to say A prime. My rule is I'm negating the x values, so that's negative 1, 2. B prime would be negative 3, 4. And C prime would be negative 4, negative 3. And if you compare that to our graph, the coordinates match up. Okay, points can also be reflected over other lines, not just the 4 special ones. So here's an example. We want to reflect the point 5, 4 over the line x is equal to 2. So I drew an x and y axis, and the line x is equal to 2, that's a vertical line. So here's what that looks like. Here's my line x is equal to 2. And my point, 1, 2, 3, 4, 5, 1, 2, 3, 4. There's my point 5, 4. Okay, if I'm reflecting over that line, it's going to be the same distance away on the opposite side. So you basically count the distance to the line and move the same on the other side. So my new point's going to be right there. 1, 2, 3, 1, 2, 3, and there it is. And that point is now negative 1, 4. So that's how you do it visually. You could also just kind of do this in your head. If I'm reflecting over x equals 2, that means that's parallel to the y-axis. That means the only thing changing is going to be the x value, and the y value will stay the same. So you could figure out the distance between 2 and 5, and then to get from 5 to 2, you got to subtract 3, so you subtract another 3, and that's how you get to the -1. But the y value stays the same. I find it always good to at least sketch a graph. It doesn't have to be super accurate, just to double check. So just to write down some notes, you would find the distance from the point to the line of reflection, and you would move that same distance on the opposite side of the line. That works if we're reflecting over an x equals equation or a y equals equation. You would do the same kind of process. Okay, we also want to define an isometry. Isometry means that it's the same size and shape, so those things don't change. Okay, and then we have direct isometry and opposite isometry. So a direct isometry, that means the orientation stays the same. Okay, so the order of the letters doesn't change. If I have triangle ABC and I translate it, A prime, B prime, C prime, if you look at the order of the letters, A, B, C goes around counterclockwise, A prime, B prime, C prime goes around counterclockwise. Okay, that's a direct isometry. And then we have an opposite isometry. Sometimes it's called indirect, sometimes it's called opposite. So indirect or opposite. And that's when the orientation changes. Okay, so that's when you have a reflection. If I have triangle ABC and I reflect it over a line, then I get a mirror image, A prime, B prime, C prime, and the orientation changes. Here, if I start off counterclockwise, now it's clockwise. So an indirect isometry, really reflections are the only ones that do that. If I reflect something once, it's going to flip. So it's going to change it has an opposite isometry. Direct would be translations and rotations. Neither one of those flips it. So they still have the direct isometry. Finally, we have lines of symmetry within a figure. So each line of symmetry will divide a figure into congruent halves. And figures can have more than one line of symmetry. Basically, you're able to fold an image over a line of symmetry and the two sides would match exactly. So for example, a rectangle. If this is a rectangle, I can draw a line of symmetry down the middle vertically and also horizontally. Both of those I'm able to create, I'm able to fold over those lines and the sides would match exactly. So a rectangle has two lines of symmetry. A parallelogram, though, we have to be careful. A parallelogram has no lines of symmetry, because if I tried to draw one on here, even if you think like diagonally, if you folded that, you would have cat ears. They wouldn't match. So there are no lines of symmetry for a parallelogram. And then finally, we have regular polygons. A regular polygon means all the sides are the same length. So in a regular polygon, the sides and the interior angles are all the same. So the number of lines of symmetry is going to be equal to the number of sides. Okay, so you have to remember your regular polygons. There's a pentagon and hexagon and octagon and nonagon, so we have to remember those. But the number of lines of symmetry is equal to the number of sides. So let's look at a pentagon, and we're going to call it a regular pentagon, even though I probably don't draw it very well. I suppose I could upload a shape, but that's the best I can do. We're going to assume that all the sides are the same length, even though it doesn't look like that because I'm not very good at drawing this. And if I'm going to draw the lines of symmetry, I can go through the vertex right there. That would split, that would create two congruent sides. And again, assuming my picture was a little bit better, I'm a little off. But you can always draw, you go through each vertex, and there are 5 lines of symmetry. Okay, so that is a quick rundown of reflections, line reflections, and lines of symmetry.